And good evening, AP Physics students. Got a good problem for you tonight from Chapter 21 about electromotive forces and, boy, just everything we know about electricity and magnetism in one problem. I'm excited. Let's get going. Let's look at the picture here. There's a picture for this problem, but there's a better one in the book. And it's up at the top here. And we have a wire, black wire here that's in a magnetic field, and the magnetic field is coming out of the page. And we have a bar lying across it. And the bar is going to get pulled to the right with some speed v. Okay? So this is kind of the setup of the problem. We're told the distance between the wires here is 0.12 meters. The bar is being pulled to the right at 0.15 meters per second, 15 centimeters per second. The magnetic field in this region is out of the page, and it's 0.8 Tesla. And the problem tells us that an EMF is produced when the bar is pulled to the right. How big is that EMF? Well, first of all, let's talk about why is an EMF produced. Well, recall that we have a flux here, a magnetic field pointing out of the page, and we have an area here, and the area is getting bigger since the bar is moving to the right. You can think about it as there'd be more magnetic field lines being enclosed. So kind of an unusual thing. Remember, flux is magnetic field times area. And so far, our problems have dealt with a change in flux because the magnetic field is changing. But just as easily, the area could change, and that can create a changing flux too. And of course, we know by Faraday's law of induction that a changing flux will produce an EMF. Well, let's write down Faraday's law of induction here. We just have one loop here, and we'll deal with the direction in a minute here. But we know that an induced EMF is equal to the rate of change of magnetic flux. Well, what is this? Well, change in flux is final flux minus initial flux. So I'm going to write this as magnetic field times the final area minus magnetic field times the initial area, right? So over time, the area that the loop is enclosing is increasing. So the magnetic field itself is constant, but the area is changing. Well, how much is it changing by? Well, as this bar moves to the right, at some time later, the bar, let me see if I can draw this in. The bar sometime later, say delta t later, is going to be over here. How much more area is this? Well, in some amount of time, it will have moved to the right a distance v times delta t, right? Distance is speed times time. Well, and if it's moved that much further to the right, then the area would be that length times this length, right? The area of this guy here, the change in area, would be this length times v times delta L, v times delta t, right? So I'm going to claim here that this new area is equal to v times delta t times L. So I'm going to claim here that my induced EMF is going to be equal to B times, I'm going to factor out a B. The final area is going to be the initial area plus V times delta T times L. So the final area is the initial area plus this. And then, of course, we have minus the initial area, all divided by delta T. Okay? Now, simplifying here, it looks like the initial area goes away, And I am left with that the EMF is equal to B times V times delta T times L divided by delta T, or E is equal to BLV. And as a matter of fact, that equation right there is actually the last equation on your equation sheet underneath the electricity and magnetism section. So congratulations there, ladies and gentlemen. So let's finish off this problem here. The induced EMF is equal to the magnitude of the magnetic field, 0.80 Teslas, times the length of the bar here, which is 0.12 meters, times the speed, which is 0.15 meters per second. So we get an induced EMF of 0.0144 volts, which is the answer to part A of our problem. Okay? Nice work. Part B. Part B says, what is the direction of the electric field felt by the electrons that are in this bar? So we know we have an induced voltage, and whenever you have voltage changes, you have an electric field. Okay? Well, we can use our equation. Electric field is change in voltage per unit distance. And if we plug that in, we know our change in voltage here across the bar, 0.0144 volts. That's just our EMF. And our distance is 0.12 meters. Therefore, the electric field felt by the electrons is 0.12 volts per meter. But we're not quite done because we need to know a direction here of the electric field. So let's find out the direction here. So I have a flux pointing out of the page. As this bar moves to the right, the amount of flux is increasing out of the page. So the direction of the change in flux is also out of the page. If you go from flux being out of the page to bigger out of the page, that's a change in flux out of the page. So the direction of the change in flux is out of the page. Therefore, by Lenz's law, the induced current will have to produce a magnetic field into the page. So I claim that the current in this bar must be going this way. Okay? Because if the current was going this way, if I did my first right-hand rule, okay, that would produce a magnetic field inside this area into the page. And by Lenz's law, the induced current produces a magnetic field that opposes the change. So since the change is out of the page, the induced current must produce a magnetic field into the page. And if that is the case, that means that the current is flowing down this way or downward, and that must be the direction of the electric field. So the electric field here is towards the bottom of the page or downward. Now notice I don't really like the way the question is phrased by the book. It said, what direction do the electrons feel an electric field? Well, the electric field is pointing this way. That is the direction of the electric field. Of course, we all know then that an electron would experience a force in the opposite direction. So I'm just going to write that electrons feel electric field force, can you guys read this? Upward. Because it's kind of a confusing question. The direction of the electric field here would be towards the bottom of the page, but an electron would feel a force upwards. All right. Nice job, physics students. That was a really tough problem. Sometimes people ask me, Mr. Kirsten, wow, that was a lot of physics. How did you get to know so much physics? Well, a lot of hard work, and all along the way, my family really helped out with always challenging me to get my brain going whenever they could. My grandfather would give me problems to do all the time when he would come over, and it was just very cool. And I wanted to show you something I got for Christmas a couple years ago from my uncle, who's an engineer. He gave me, isn't this a nice present? Look at this. This is a $100 bill. My uncle gave me $100. Look at that. Isn't that cool? Right? But of course, nothing in life is free. So even though he gave me $100, he said, "All right, Jeremy," that's what my family calls me. You have to work for it. You have to do a puzzle before you get your Christmas present. And of course, this was a couple years ago, and I still haven't gotten the puzzle or had time to. So there you go. You have to get the ball. You have to get the ball in right there to get the springs so that it'll open. So there you go. Always be challenging yourself. Always be thinking. And you will be rewarded with it. Probably with a lot more than $100 because you'll know that you challenged yourself and did well. All right. Nice work, AP Physics students. We'll see you tomorrow.